is the solution process notes. So we're gonna keep going. Alright, so a saturated solution. So we're gonna talk about saturated, unsaturated, and supersaturated. Those three terms. Alright, so a saturated solution. Alright, so remember, a solution is when we have a solute dissolved in solvent. Okay? So this is a solution that contains the maximum amount of dissolved solute. The maximum amount. So how can you tell if it's saturated? If we add any more solute, then it would fall to the bottom because it wouldn't dissolve. So this would be the max amount. So it's still dissolved in there, okay? None of it has fallen to the bottom yet. If we added more, it would fall to the bottom because it would not be able to dissolve, okay? So saturated means that this is the maximum amount of dissolved solute. Maximum amount. So at least have out either some paper for notes or at least have out the notes looking at them on your computer, one or the other. So a solution that contains the maximum amount of dissolved solute is saturated. Alright, so unsaturated would be a solution that contains less solute than the maximum it can have. So it has less than the max. It's not gonna look any different than a saturated one. It's just that if we added more, we could, and it wouldn't fall out to the bottom. So it has less solute than the maximum amount it could have. So I think of unsaturated being like, when you have Kool-Aid that's just not very sweet, you know? You could add more sugar to it, but it's like not very sweet Kool-Aid. It's unsaturated. We could always add more sugar to it and it would dissolve into it. Alright, good on that one? Alright, and then super saturated is when you have too much solute. So that would be that point where you added it past the saturated amount. So solution that contains more dissolved solute than saturated solution. So what happens is that you're gonna have that falls out. Super saturated. I don't know if this link works. Let's try it. It says watch. We're gonna try.
Oh, wow.
That's just not bad.
Well, what is that? Yeah, what is
Is that ice?
Sodium acetate.
Oh.
What is that?
So they had warm water because it was 52 degrees Celsius, room temperature is 24 degrees Celsius. So that was warm water. Put sodium acetate into
Fingers are
it,
caught in
and it
Oh, it's hard.
immediately
Ooh.
turned to a solid.
That's like the thing you can do with ice. You like almost freeze it and then you like smack it and it like freezes really fast.
Can we do that?
I don't know, I would need to try it
Is it
first.
edible?
You should try it like in front of us. You should try it in front of us.
I don't know, let me practice it first.
Make an art contest.
This is the first time I'm watching this video. I didn't even know if the link worked, so.
Now make an art contest out of it.
Like I'm telling you, I'm using the straight slides that the teacher who taught this through Campbellsville uses, so. That's why sometimes I don't know what slide is coming next.
Super saturated.
Bro.
That's actually cool.
Wow. So like it
We'll just
reacts
touch
to
it.
the skin.
But it's not frozen.
Look at the reflection of his face.
I like the lines.
People are gonna have a lot of fun there with that.
I know I'm smart, but don't do this.
Alright, well,
She's smart.
it's not what we're supposed to happen.
It was in the when you run out of gas. Like, you set it
It's the worst thing ever.
Yeah. Dang, 8,000. Appreciate it, you just give me
For me?
25, whatever, 25, not
For me?
20.
Dang, Joey. Just give me a couple million and like 250 gold.
Oh, yeah. I appreciate that. Yeah, I'm going for it.
Alright. So,
Whatever.
non-polar solvents. So, do you think water is polar? Because we talked about water being the universal solvent. Do you think water is polar? We have hydrogen over here, oxygen over there. Remember we talked about polar being different? Do you think that is polar? Yes, so water is polar. It has different poles, okay? So a non-polar solvent, alright? So we use the rule like dissolves like, alright? So ionic compounds are not soluble in non-polar solvents because, think about it, like dissolves like. So if something is polar, it has opposite ends, okay? Well, so does ionic, right? Because we have ions, opposites. So like dissolves like. So ionic is opposites because you have a positive and a negative. So this would be opposites. And you have polar, which is also opposites because you have a big electronegativity difference. So this would be like dissolves like. So polar dissolves ionic compounds, all right? But non-polar solvents, if they're not polar, is it gonna dissolve something that has opposite ends? No, because like dissolves like, and those aren't gonna be the same, because non-polar is not opposite. So it's not gonna dissolve an ionic compound, that's what this is saying. So non-polar solvents are not going to dissolve ionic compounds. So ionic compounds are not soluble in a non-polar solvent. So just remember, what I would write down is that like dissolves like. So what if you had a question on a test? Which compound could dissolve in water? And your options were, let's see here.
So non-ionic or ionic would dissolve which lead?
Which one would not dissolve in water?
Not.
Ashley,
The bottom. You know. Actually, no, that would because it's on the opposite side of.
so which one would not dissolve in water? So remember, like dissolves like, so we know that water is polar. Alright, water has opposites. So we know ionic would dissolve in water, so which ones are ionic up there? So remember, ionic is metal, non-metal, which ones are those? NaCl and PbCl2, so those two would dissolve in water. Which other one would dissolve in water because it's polar? It's not ionic, but it's polar. HCl, because opposite sides of the periodic table. Hydrochloric acid is going to dissolve in water because it's polar, opposite sides of the periodic table. Which one is non-polar? NO2. And we could draw it out and see that it's non-polar, but we don't need to. It's non-polar. Okay?
Wait.
Two elements side by side right there, periodic table. They're not going to have very strong electronegativity differences. So it would be non-polar. Okay? Alright. Alright, so two new terms, miscible versus immiscible. So miscible just means that they are liquids that freely dissolve in one another. Immiscible is liquid solutes and solvents that are not soluble in each other. So what are two immiscible liquids?
Oil and water.
Oil and, well, probably water, yeah. If you let it settle over time, they're not gonna mix. But what are like two really good ones? Oil and, what's the lighter one? Less dense. Vinegar, right? That's like the classic one, right? Oil and vinegar does not mix, right? So oil and vinegar are immiscible. We can put them together, but they don't have the same density. So typically what causes something to be immiscible? A difference in densities. Because one is gonna have a lighter density, one has a heavier density. So if we let them sit, they don't mix together because the lighter density would go to the top, the heavier density would go to the bottom. If they're miscible, that means they dissolve into each other. So immiscible means that they do not dissolve into each other. Two liquids that don't dissolve into each other, so we're talking about liquids. Miscible means that they do. Miss Elmore likes mixing peach monster and orange juice together. That would make them miscible, right? Two liquids mixing together, they would be miscible. It's actually really tasty. Two liquids that dissolve into one another, miscible. If they don't, they settle out, they won't dissolve into each other, immiscible, like oil and vinegar. You got miscible versus immiscible? Okay. Alright, so we're gonna talk about how heat and pressure affect solubility. Alright, so let's talk about pressure. So solubility, remember, is solute dissolved in solvent. Okay, so remember, we got particles dissolved into our solvent. Alright, so pressure. How would a change in pressure affect our dissolvedness? Okay, solubility. I'm trying to use a different word besides solubility so you know what I'm talking about. Dissolvedness. How would pressure affect how much is dissolved? What is dissolved? Okay? So pressure changes have very little effect on solubilities of liquids and solids. It mostly affects gases. That's a key thing you need to know. I feel like if I'm recalling, that's a test question. I would make sure you have that written down, or you have indicated that in some way, shape, or form. Pressure does not affect the solubility of liquids and solids. Pressure affects the solubility in gases. Let me see if it's on the next slide. Yeah, okay. Alright, so let you write that first. I didn't want to get ahead of myself.
So what did you say to write down for the recon test?
That it does not affect, pressure only affects gases.
Pressure only affects gases.
Solubility in gases. It won't affect the solubility in a solid or liquid. It only affects solubility of gases. So we're talking about a gas solution.
Joey, I'm out of rolls. So unfortunately. No. I'm like 300 like little thingies away from getting home 3 more rolls, but I don't have any rolls.
What is she? The parade.
Alright, and what is going to explain that is called Henry's Law. Alright, so when we talk about the solubility of a gas with pressure. Alright, so it says the solubility of a gas in a liquid. No. Why does it say liquid? Go back over here. Why is it talking about liquid?
Gas in it. Is it not liquid?
Shouldn't be. Why is it talking about liquid? Should just be.
So what's your,
Yes.
Solubility of gas in a liquid.
should we write it like gas and liquid or not?
I mean, that makes sense, but okay, this is talking about that. Well, it only affects the gas part of it, but it could be a gas and a liquid. Okay. Alright, so what's happening? Because it's only affecting the gas part, the carbon dioxide. Okay, the gas particles. Alright, so think about it. If you increase pressure, so you increase the pressure of something, what's gonna happen to your particles in a gas? They get closer, they start moving faster, right? Alright, so when you do that, alright, if your particles are moving faster, what did we say that they do with the solvent?
Dissolve easier.
They're gonna dissolve more. Alright, so it says the solubility of a gas in a liquid is directly proportional to the partial pressure of the gas on the surface. So think sodas. The solubility of carbon dioxide is increased by increasing pressure. Because once you increase that pressure, your particles start moving more. They come into contact more with the solvent, so more particles are gonna dissolve. So the more you increase pressure, the more particles that dissolve, so the more soluble or the higher concentration you're gonna have.
So like, if you were to get to a point of something that's no longer soluble because there's too much, then you were to increase the pressure, would it like go past whatever that too much is?
Yeah, I guess it would become super saturated because you would have too much of it.
Oh, okay.
So the solubility of the gas is increased by increasing pressure. So higher pressure, higher solubility. So they're directly proportional. Yes.
So is it like when you have like an empty water bottle, and you start like, like twisting it and like it starts like building up more pressure? It's kind of like that.
Well, yeah, because in that case, you're also decreasing the amount of volume in your container, and that's why it's gonna build up the pressure, because it's got less room for that to move, because when you twist in it, you now have less room for the particles to move in there. So increasing the pressure, because here we're increasing the pressure, the particles start to move faster, they come into contact more with the solvent, so more of them is gonna dissolve into our solvent. Because when our particles come into contact with the solvent, that's when they dissolve. So they're directly proportional. Increased pressure, increased solubility. Now, would this happen with two liquids?
No.
Would this happen with a solid and a liquid?
No.
No, it only changes gases. So what's happening is it's changing the carbon dioxide. All right, this wouldn't happen if I didn't have a gas, because it can't change the pressure of two liquids. It can't change the pressure if I had sand going in my water. It's not gonna change anything. What's changing is the gas particles. We can only change the pressure of gas particles. It's the carbon dioxide particles that are getting pushed closer together and they start moving faster, and that's when they're hitting the solvent and then dissolving into the solvent, okay? So it's only the gas that's affected by pressure, okay? Only gas. And that's Henry's law. Increased pressure, increased solubility of a gas. All right? And this would apply if I had two gases too, right? Because if my gas particles start moving together and they start hitting each other, aren't they gonna dissolve into each other? Yeah, so it would apply with two gases too. I don't know, I can't think off the top of my head where that would apply with a gas and a solid. So I mean, I could see gas and liquid or gas and gas. Can't see gas and solid. So this is called effervescence, when you have a rapid escape of a gas from a liquid. So when your drink fizzes. When your drink is fizzing, so you have that rapid escape of the gas. So when you open up your Coke, or I open up my Mountain Dews, that is technically called effervescence. Such a pretty name.
It's a long
How
name.
is that effervescent in swimming?
Yep, that is the rapid escape of gas from a liquid. So when you have your Mountain Dew,
Your deep gas escaping.
right? So right now,
Well, great.
have my carbon dioxide is dissolved in my drink, okay? But when I open it, it is now coming out. Oh, so sad, it didn't very much. But do you see there's a little fizz? So it's now coming out. It was dissolved in there, now it's coming out, and that is effervescence. The carbon dioxide that is now coming out of my drink.
So what is it whenever like you open it and it just starts fizzing?
Well, if I had shaken this before, which I don't want to do that, but if I had shaken it up, it would definitely come out. A lot more carbon dioxide would have came out that was dissolved. But I don't want to do that, because I'm going to drink that. But yes, so that fizz, or you know, if you drop your drink and then open it and a bunch comes out, that is called effervescence.
And then
Fancy
whenever,
name.
you know, whenever like you shake a soda so much it gets flat.
Is it like if you sit, it's probably, well, does
Well,
it
like
come
if it's-
out, like seep out maybe?
Like, so like if you had a bottle, I don't know if it's like matters if it's opened or not, but if like you let it sit out and it just sits there for a while.
It becomes flat like a
and it
square.
becomes
Well, I'll
flat,
tell you,
yeah.
I'll tell you that like, if you, like a 2 liter, once you open a 2 liter, like it's open, even though if you put the lid back on it, like it's gonna seep out. And so you can like put it in the fridge, it doesn't matter what you do, it's seeping out of it. So that's why it's gonna go flat in a day or two, cause it's not,
See,
it's, cause once you've opened it, it's not dissolved anymore, like it was before. And so it's gonna seep out, the carbon dioxide is coming out, and that's why it's gonna go flat. Alright. Okay, so now let's talk about temperature. So we talked about pressure, let's talk about temperature and solubility. What do you think happens when you increase temperature? What's gonna happen to solubility? It's gonna increase, because what are your particles gonna do when you increase temperature? They move faster, and when they move faster, they come into contact with the solvent more, and then they dissolve more quicker, so they are more soluble. So, increasing temperature. Alright, so solids and liquids. Increasing the temperature increases solubility. Alright, now, this one always gets me. And like I said, I didn't make these notes. Because I would think that increasing the temperature, even in a gas, is going to increase the solubility. Because your particles are moving. So maybe we should fact check this.
Cause isn't,
Because I feel like it should increase it. I feel like I did this last year when these notes came up.
isn't the increase of temperature cause more pressure? Cause like,
Let's look it up.
never mind.
Increasing temperature.
How do you get more rules? You probably got the 1,200 thing.
Florida State University, as
I got that
temperature
as well,
increases, the
that's why I got
solubility
all
of
my
the gas
rules.
increases,
900.
as shown by the downward trend in the graph.
Are you going for William?
Huh?
For William?
I work.
There you go.
Alright, well, it's true, and I want an explanation, because it doesn't make sense to me. Okay, well, this one says the opposite.
I don't either, but you know. I agree with you.
The colors.
We might win. That's what they told me.
Well, how do you afford to go to Albany? Oh wait, you're an athlete, you gotta go free.
Feel free.
Oh, hands down.
Yeah.
This says increased temperature causes an increase in kinetic energy. The higher kinetic energy causes more motion in the gas molecules to break intermolecule bonds and escape the solution. I don't know what that means. It's from the Florida State University.
So they escape, and that's why?
Yeah.
Moving too much.
But with pressure, it made it increase. And they were moving.
I think pressure.
I guess this is talking about like in an open system, and with pressure it was in a closed system?
Yeah, I was thinking it's
Yeah.
because it's closing the ball.
Okay, alright, well, that's the only explanation I got, okay? So, alright, let's go back. So notice with pressure, when we increase pressure, it has to be in a closed system. See how this is a closed system? Because if we increase pressure, it has to be increased in something, right? We're increasing the pressure in something. Alright, if we increase temperature, we could just like increase temperature in this classroom of gas, of the air, right? So if we increase the temperature of the gas in this classroom, our particles would start moving more. But I guess what, based off that explanation, our particles would obviously start moving faster, but they wouldn't necessarily come into contact with each other. If it was an open system instead of like a closed container system. That's what I'm getting from it. I'll try and look it up more to give you a better explanation, but like I said, that one has never made sense to me. Because to me, you're still increasing your particle speed, but what it's saying is that your particles are now not coming into contact with each other
Well, it
because
just-
they're increasing
It
in
just
speed.
says They break intermolecule bonds, causing them to escape solution.
Yeah, so they go out of it. So I don't know, just write it down. Write it down. So solids and liquids, increasing temperature, increasing solubility, but in gases it decreases. So write that down. Yeah.
For the solid and liquid, it says not always. What situation would it be?
Or just write it always does. Yeah.
Oh, always.
Yeah, put it always does. Yeah. And I think about it as anytime we want, there are some chemicals that you don't want to heat when you are mixing them with water, but it is very few. Most of them, if you want to increase the dissolving and increase the solubility, how much is in it, you add heat to it. So in most cases, which is the majority of them, it's gonna increase temperature, increasing temperature is gonna increase your solubility. This one, I would just write it and I'll Google it. I will try and get a good, maybe I'll try and find a YouTube video on it or something. Alright. So, cause that's what I need a YouTube video on
This
it.
is such a long subject.
Yeah, there's lots of definition type ones on this. Alright, so we're finally getting to the math part of this unit. Alright, so concentration is the measure of the amount of solute in a given solvent. It's just the name of it, concentration. So how much solute you have in your solution. So the measure of the amount of solute in a given solvent. So if I say something is diluted, what did I do to it? If I diluted something, what did I do?
Decreases concentration.
I decreased the concentration by adding what?
Water.
Water. So if I dilute my Kool-Aid, I added water to it and I decreased the amount of solute that I had. Well, I didn't really technically decrease it. I increased the amount of solvent, which made my solute not as much. If I make it more concentrated, I add more solute. If I make it more diluted, I add more solvent.
Teachers, there was an email sent out by Ms. Cheapwood for those juniors that was interested in GSP to report to the library at this time. An email that was sent out by Ms. Cheapwood.
Did you make GSP?
Any juniors that was interested in GSP, please report to the library at this time.
Alright, so for concentration, there's two ways we can express it. We can express it in molarity or molality. We're going to be focusing on molarity. So we're going to be focusing on this one, molarity. Alright, the difference is when we calculate molarity, it's moles per liter. And when you calculate molality, it's moles per kilogram. Well, when we're using water as our solvent, which one would we probably measure our water in? Liters or kilograms? Liters. So that's why we use molarity, not molality. It just makes more sense, because if we're measuring water as our solvent, we would use liters, not kilograms. So we're going to be using molarity. That's what we're going to calculate. Alright, so we're going to be measuring concentration by calculating molarity. Alright, so molarity, like I said, is moles per liter. So it's the number of moles in 1 liter of solution. So the number of moles in 1 liter of solution. So have you all ever been in the lab and on the bottle of chemical it said like 1M and then the chemical's name, or 0.5M or 0.1M?
Yeah.
That was the concentration of the chemical in molarity. So if it's 1 molar, or if it's 0.1 molar, or 0.5 molar, which one was the most concentrated? The 1 molar versus the 0.1 molar, which is not as concentrated. So last year I did a lab with some vinegar that smelled up the whole school, and it was 13 point something molar. Very concentrated, right?
Was that the
Yeah.
vinegar
Super
you said?
concentrated. It was just vinegar, but it was burning kids' eyes.
I
Cause
remember
it was
smelling-
very concentrated. I should have diluted. Next day I diluted it down.
I remember smelling a lot of vinegar in like one of the hallways.
That was it. That was my lab. Yep, it was over in Miss Lynn's classroom.
Figures.
I was kicked out of my room, so I just grabbed the chemical real quick, and yeah, I thought the stronger the base, the better it would work, and that was a lie.
Learn from your mistakes.
All right, so our first practice problem here. So it says, you have 3.5 liters of a solution that contains 90 grams of sodium chloride. What is the molarity of that solution? All right, so what info do we have here? We have the liters, so we have our liters of solution already.
Turn the grams into moles.
Yep, and we have our grams. So we gotta turn our grams into moles.
So we already have like the bottom of it, 1.50.
Yeah, so we already have the bottom.
Okay.
We just gotta find moles because we were given grams. So we're gonna start with our 90 grams of sodium chloride, and we have to convert that to moles. So I'm gonna bring my grams of sodium chloride down here. And how many moles of sodium chloride would that be for? 1 mole of NaCl. So real quickly, find the mass of sodium chloride.
Number.
58.43.
58.43?
Yeah, rounded.
You guys good with that mass?
Yes.
Alright, so now you take your 90 divided by 58.43 and tell me how many moles that would be. 1.5?
Did you get that?
Yeah, 1.5 for it.
54, and that would be moles of NaCl. Alright, so now we're gonna plug that into our molarity formula. So our molarity equals our 1.54 moles over our 3.5 liters. 0.44?
Yes.
Alright, so now units. So we want molarity. So the units for molarity is capital M. So capital M, so molar, that's what that stands for. So it's 0.44 molar. And then we put of what? So NaCl. 0.44 molar NaCl.
That's not that bad. So anytime you give a gram, you just change it to
You
mole.
gotta get it to moles. Put it in your formula.
Is this as complicated as it gets?
Yeah, it's just like variations of this. But it's always this formula.
Okay.
Alright, so you try this one. So you have 8 liters of a solution that contains 50 grams of potassium bromide. What's the molarity of that solution? So you do that one on your own.
2 grams.
I didn't think you would have like the atomic mass of everything. This ain't a lot of work that I did out
When? extras.
Yeah.
Actually, no, cause I just did a. I'm very specific about the weight.
I mean, that's what extras.
I don't do bolts until I get.
I only did it so I could, cause I knew how to get, I hoped to, but I would get one. So I get
What do you don't know?
My doctor said it was sensory issue.
for the giant bronze, for bronze nine, for them.
No, you can't trade golds anymore. You can't trade golds.
Do you have, Moiner, the adventure of gold?
Zero
Middle
point
one?
zero five.
Yeah.
It's like,
I need God of Thunder, but.
For the third one, no, that's also gold. Which one do you need for third one? I need that, I don't know.
What do you need for it?
I'm a gold one. Robin Hood. What do you need?
I need the.
I need a good book. Need the first one.
All the answers.
Extras on all of.
Alright, I need a gold one, but I can give you that.
That's the worst one.
So, that one.
And then there's a cat on there, they can trade it.
I can trade
Oh,
this one
it's so
out.
bad, some of their families don't visit.
Here, wait, I'm not gonna trade it
We
yet.
have a resident,
Like,
she
I'll
was
still
like
have the 89.
and she would, she just
Yeah, the.
bawled and
Right, on that one.
so like,
Yeah.
what's wrong? And she said,
Yeah, so I'll get that one, so you can even it out.
Your answer.
sit here and tell me the stories, what are you talking about?
Alright, so we start with our 50 grams of potassium bromide. And then, what is it, 119?
Yes.
So 119 grams of KBR
Oh, I didn't want to.
for 1 mole of KBR.
I wrote that.
And what'd you get for the answer there?
0.42.
0.42. And that's moles of KBR. And then we plug that into our formula up here. So we would have 0.42 moles divided by our 8 liters. And what'd you get?
0.0528.
So 0.053.
Yeah, you can, yeah.
Alright, and then what would be the unit?
Molarity.
Molar, right?
KBR,
Molar.
KBR.
And then KBR.
Said mole.
There you go.
Unbelievably tired.
Good with that? Not too bad, right? Is everybody good on this part, right? Cause this was from the last test. Is everybody good on that conversion?
Is there gonna be any two-step conversions, like, they give us stuff, thank God?
Are we ever gonna have to find liters? Like,
You might be given milliliters.
okay.
But
We'll just have to.
we'll practice that.
Okay.
Okay, that's what's up.
'Cause I know
That's not that bad.
Like on this one.
1,000 nano.
Alright, so next one, it says, what is the molarity of a solution composed of 98.6 grams of rubidium sulfide dissolved in enough water to make 500 milliliters of solution?
So how many milliliters are in a liter?
Alright, so we have our grams this time, so we know we gotta convert to moles. Alright, so we have this.
So,
But we have 500 milliliters this time, and we need it to be in what?
Liters.
Liters. So what's that conversion? Milli. What does milli stand for? What number? 1,000, right? And is it 1,000 times larger or smaller than a liter? Smaller. So if I had a 500 milliliters,
5 liters.
and I put milliliter down here and liter up here, which is larger?
Liter.
Liter, and milli stands for 1,000. So I would have to divide by 1,000. So what's my answer?
0.5.
0.5 liters. So
Oh.
now you have that starting volume. So if you ever have milli, because that's the only other unit you would be given, milli, because that's what we measure in the lab, is milliliters, right? It's very rare that in the lab you would measure liters. So a lot of times you're given milliliters. If you're ever given that, just move your decimal to the left 3 times. That's it. Decimal to the left 3 times. So we've got our starting volume, and we've got our 98.6 grams of RB2S.
Oh crap, I did that wrong.
So our grams of Rb2s for our 1 mole of Rb2s. Anybody got the mass of Rb2s?
203.
203?
Yes.
Yeah.
So 98.6 divided by 203?
No.
0.48 or 0.49.
49?
Yeah.
Alright, and that would be our moles. So now we just have to plug it into our formula. We got our liters, we got our moles. We know our answer is going to be pretty close to 1. So 0.49 moles divided by our 0.5 liters. And what do we get? 0.98.
Yes.
Capital M for molar. And then RB2S.
Do we have to put RB2S anytime like next to the 0.49 mole?
No, we didn't put it there, cause this is your final answer. If it says, what's the molarity, this is your final answer.
Okay.
Okay. We good? Good with that?
So,
Everyone's been on it, so.
how?
Alright, so this time it's a little different. So this time it says, you have 0.35 liters of a 1.3 molar hydrochloric acid solution. How many moles of HCl does this solution contain and how many grams?
Wouldn't you just,
You just put it.
So
in.
think about it. Your equation is molarity, oh gosh, molarity equals moles over liters. So if I want to find moles, what's my formula?
You just put the.
Oh, you just-
Moles equals
It'd be, capital M times liters.
moles times liters, right? This times that would give me that, right? What would my formula for liters be?
Replace liters with moles, or moles
Would be odd.
Definitely not split.
There you go.
Moles over molarity.
oh,
Think about it, the triangle. Triangle. So if you're looking for molarity, it's moles over liter. If you're looking for moles, it's moles times liter. If you're looking for liters, it's moles over molarity. So use the triangle. Okay. Alright, so we're looking for moles. So our moles are going to equal our molarity, which is 1.3 molar, times our volume, which is 0.35 liters. So our first answer is, what'd you get? 0.45? And that would be, because we're looking for moles, so that unit would be moles. And that's HCl. So that's our first answer, right? But this is a two-part question, because what else is it asking us for? How many grams? So we're kind of working backwards on this one. So we got our moles, but now it wants us to find how many grams that would be. So what do I do now?
We do the conversion chart.
Yeah, so it's kind of like a backwards conversion of what we've been doing. So now I'm going to start with my moles. So 0.45 moles of HCl. And I'm just going to do backwards of what I've been doing. So my moles of 1 mole of HCl goes down here.
And 1 gram of HCl.
Not 1. I got to find the mass of it. So what would the mass of HCl be?
like 36.
36.46.
Do the math in your head.
And then you should.
That's crazy.
So this time we would multiply our mass of HCl times our 0.45 moles. And what do you get?
16.59.
16.4.
I got 4 and 6.4.
I added the exact numbers, so,
Did you do 36.46 times 0.45?
I mean, I added,
You use the full number.
Yeah.
So I'm just gonna go with 4
Yeah, 16.4.
for these numbers. Alright, and then my moles cancel out. And what units would be left?
Grams.
Grams of HCl. So I have two answers, because it asked me how many moles, there's my first answer, and how many grams, there's my second answer. Good with that one?
Yes.
So it's just finding a different part of the equation, because on the first couple examples, we were finding molarity. This time we were finding moles and then grams. Good?
Yeah.
C.
I think I got one more. And I'm sure it's calculating volume. Alright, so it says, what volume of 1.6 molar CSF is needed for a reaction that requires 394 grams of CSF? So this time we're looking for volume. So what's the formula for volume using that equation? What did we say it was? Liters equals what? Moles over molarity. So we have grams, so we know we gotta get that to moles. Do we have the molarity?
Yes.
Yeah, we already got that. So we just gotta get our grams to moles, and then we'll plug it into our formula. So let's start with our 394 grams of CSF. And let's get that to moles first. So our grams of CSF down here, and that's for 1 mole of CSF. So what's our mass of CSF?
Can we just do both?
We'll at least go to like 1 or 2 decimal places. 132.9?
That's just CS.
Oh, did you do F2?
Oh.
I thought you just asked for CS.
And F, CSF.
My bad.
You're good.
So 150 is 132 plus 18, so
18.99.
She wants the decimals too, that's
Oh,
why I was
151.89.
Yeah.
Alright, so now we divide 394 by 151.89, and what do you get?
2.47.
2.47? And that would,
Oh, I put it in the wrong
Yeah, 2.59.
oh my god.
2.59. So my grams cancel out, I'm left with my moles there. Alright, so I got my mole number, I got my molarity, now I just plug it in. So 2.59 moles divided by my molarity, which is 1.6 molar. And what do we get for our volume? I feel like it should be 1 point
It's
something.
like 1.6.
1.6?
Yeah.
Is it?
2.59
Yeah, 1.6.
divided by
Huh.
1.6.
So this is exactly half
Yeah.
of that? Well, you know. Alright, and that would be liters of
I got
C.
1.6.
So you could be solving for molarity, you could be solving for moles and then grams, you could be solving for volume, but you're using that molarity formula to solve for each one. So just a 3 variable formula. Only conversion you might have to do is grams to moles or moles to grams, or getting something out of milliliters to make sure it's in liters for the formula.
Now just move it 3 times.
Yeah, move it 3 times to the left to get it out of milliliters. Okay? Questions? I'm pretty sure that's it. Oh, look, I don't even have another slide. Alright, so let me see what I got here for you.